Hi, Terrence O'Hanlon, CEO and publisher at Reliability Web and Uptime Magazine. And if you haven't noticed, this industry is moving fast as we learn more about the industrial Internet of Things, artificial intelligence, machine learning, predictive analytics. There's so much going on, not to mention the security concerns with connecting to the edge or connecting to the cloud. And we're trying to do our own learning and bring you along with that as we learn what's working when it comes to enhancing reliability and asset management. So join us for the AI and IoT technology showcase session. And what happens is we're teaching a little bit about the basics on how to use IoT and AI to advance reliability and asset management, as well as giving small technology solution providers, as well as the large technology solution providers, a chance to do a short presentation so we can quickly get up to speed with all the choices, all the innovations that are currently available to us to get us up into the cloud, to do so in a safe way, and to do so in a way, again, that's focused on advancing reliability and asset management. That's our focus. So I hope you'll join us for the AI and IoT Technology Showcase.
All right, thank you everyone for coming. I know it's 2 p.m. Hopefully you can stay awake. I know those steak tips, those are really good at lunch. But my name is Simon. I'm from a company called Petasense. And our goal at Petasense has always been to simplify predictive maintenance. And so the last couple of years, we've been working with a few of our customers to experiment with different ways that would make this process easier and more efficient. And around that time, too, we started noticing machine learning being very prevalent in a lot of different applications. So naturally, we wanted to see if any of those techniques that they used translate over into PDM. So today, I wanted to share with you some of the experiences that we got, some things that we've learned, and hopefully that'll help educate you as to whether machine learning is the right fit for you as well. And that pretty much sums up. It spells out my outline for my talk. I wanted to address these three major questions today. First of all, where is machine learning used today, and how do they do it? But importantly, why is it even practical for them to use machine learning? And secondly, I want to tackle the question of, like, is machine learning useful for PDM or not? What kind of techniques that is being used will be useful in the realm that we're in right now? And then lastly, I wanted to demystify some of the basic concepts of machine learning, but don't worry, it'll be at a high level. It's so that you can understand what your role is in making a machine learning program be successful. And if you guys have any questions, I'm going to try to leave about 10 minutes at the end of my presentation. Feel free to jot your questions down. I'd be happy to address them over at the end. Now, if you don't know what machine learning is a type of programming that differs from traditional programming in the sense that rather than having a person manually program a function, for instance, like a rules-based system, machine learning is what creates that program. Now, even though machine learning is very good at programming, it's still up to us humans to figure out what types of questions we want to answer. And there are a lot of good questions being asked out there. You may have heard Tesla, Google, Uber are working on self-driving vehicles. They use video and image recognition algorithms to try to get a person from point A to point B as fast as possible while simultaneously ensuring absolute safety to both the passengers and also to pedestrians that are around. You may or may not have heard about the Google's Go playing algorithm. It's really good at playing this board game that, it's interesting because only a couple of years ago, the best algorithm that was available, we're talking like post-Deep Blue for chess era, the best algorithm that was available for this couldn't even beat an average player, much less the grandmasters. But now we have an algorithm that can beat any person at this game, and that's just impressive. And then in the kitchen, you might see now that they have ovens that have cameras in them for whatever reason and allow you to see, allow the machine to also see what type of food is being put in, and it learns how to cook your food properly so the millennials don't have to do household chores anymore. So some applications are more interesting than others. Probably the most profitable area of where machine learning is being used is in the area of internet advertising. Perhaps you've heard of Amazon and Facebook tracking all your activity on their sites. And if you didn't know that, surprise, okay? Surprise, they're doing just that. They're looking, they're tracing not just what you click, but also how you scroll through their website, what images you're looking at, and everything that you're doing on that site. Now, if it makes you feel any better, it's almost certainly not a person that's going to be tracking your activity. It's going to be a machine learning algorithm. And that's because Amazon and Facebook have millions and millions of users. Most of you probably use them. And it's going to be very impractical to have a human manually try to build this digital profile of each person just so that you can better target that advertising. And that pretty much is the reason why machine learning is being used today. One of the main benefits is for scalability, right? How to take all the wealth of data that's available right now and make some useful insights out of that data. And I want to give you an example in credit card fraud, for instance. Do any of you know how many credit card transactions happen every second? It's about 10,000 credit card transactions happening every second around the world. And for a credit card company to trace all that using people, you would have to hire millions of people just to track whether a transaction is fraudulent or not. So they don't do that. Instead, they use a machine learning algorithm, an anomaly detection type algorithm, that basically pulls information about your purchasing habits, such as like what types of items you purchase, whether you like to purchase things online or offline mostly, locations where you do your purchasing. And it aggregates that data across your entire purchasing history to determine whether a particular transaction you made is fraudulent or not. And in another area is, and once something is tagged as fraudulent, that's when maybe somebody from their fraud department will take a look at that transaction to determine then, is it actually a fraudulent piece of activity? So another area that's commonly, where machine learning is commonly used is image recognition. Us humans are really good at recognizing the difference between a jacket or a dress. But machine learning algorithms now can actually look at images and pick out particular characteristics from an image to determine the difference between, say, what makes a sweater vest instead of, say, a formal vest. Okay, and once this algorithm is trained, it can classify thousands of images very, very quickly. Having a person go and do that would take an enormous amount of time, and it wouldn't be very practical either. And you can see that this is very useful in e-commerce, for instance, where you have a lot of images of different products, and you want to help customers like us try to find the product that we're looking for. And I already made fun of Facebook once, but in a more nefarious use case could be Facebook looking at your Facebook photos and trying to determine whether you like turtlenecks or not. Now, just like how the consumer world needs scalability, so will the industrial world. And right now, the industrial world is, there's new technology out there to add more and more sensors, instrument different parts of your plant. And but having all that sensor data is going to be useless unless there's someone there to interpret it. Now, even if you have a monthly program where someone comes in to look at all this data, you're going to be missing out on the wealth of data that's coming in on a daily basis. Every day data is coming in. There's maybe something that you could take action on earlier within the month. And the other thing that is hard for humans to do is to examine the relationships between multiple sensors simultaneously. For instance, one machine might be operating improperly or abnormally, but it might not be because the machine itself is is in an abnormal state, but because something maybe farther upstream may be causing the machine to behave abnormally. And so that's the point I'm trying to make, is that having all these sensors, it's just like how it's difficult to manage a bunch of credit card fraud, it's very difficult to manage all the sensor data all at once. What would be helpful is to have a machine learning algorithm help pinpoint the analysts to specific areas to focus their time on. And so that way, energy can be focused on the areas which need focusing on, and let machine learning deal with the machines that are currently looking healthy. Now, whether you should use machine learning or not will depend upon a variety of factors. But I think a good basis for any sort of decision making is to use what's called the 4M approach. Have any of you heard of the 4M approach? I can't take credit for it. I learned it from another conference, actually. It's very easy to remember. It's just make me more money. And so the basis of any sort of decision make should come down to whether it contributes to the bottom line. And for instance, for a lot of the reasons why people do predictive maintenance is to reduce unplanned downtime. For instance, if you have a power plant, an average one may be about 250 megawatts, and the cost of power about $40 per megawatt hour. If the plant encounters some unplanned shutdown of a week, we're talking about $1.68 million lost. Now, people who are in the power industry are very familiar with this concept, and as are people who are in oil and gas. Instead of megawatt hours, it's the number of barrels per day. But this is also applicable to manufacturing, for instance, the number of gadgets that you're putting out each day, or even in pharmaceuticals. Say if an HVAC equipment goes down, it requires a 2-week experiment to be rerun again, for instance. That's something that happens sometimes. And that can be really expensive. So when you're evaluating this, always look at how much downtime you're seeing on average in your past, and whichever predictive maintenance program you use, whether it's machine learning or not, evaluate how the costs and the benefits add up in your calculations. So with that being said, I want to talk a little bit about the benefits to using machine learning to help you decide this. Even if you had only just started instrumenting your plant with sensors, you can get some benefits very early on. And one of those ways, if you remember the credit card fraud anomaly detection, a similar technique can be used here, which takes multiple sensors and aggregates that to create some anomaly score, or in this case, I've called it a health score. And so that you have one single trend that tracks the health of a machine. And instead of having to look at, like maybe you've outfitted a machine trained with 10 different sensors, instead of having to look at 10 different sensors, you only have to look at this one single health trend. And once an anomaly is triggered, that's when you would call in an analyst to come take a look at that particular the data that's coming from that machine. And this is actually better than using alarms, basic alarms. But I'll explain to you a little better why later on in this presentation. Another benefit, just like we are able to classify different types of clothing, we can classify for different types of faults too. And a machine, for vibration faults, they exhibit themselves in very distinct patterns, as many of you know. And machine learning is very good at recognizing those patterns. And so once a machine algorithm is trained, it can actually provide some sort of diagnosis, and this can be integrated into your work order system, for instance, to help you make sure that the inventory for spare parts are available for whatever the diagnosis is. Long term, you get even more benefits from having machine learning. Once you have enough data, you can provide a very accurate estimate of the remaining useful life of a machine. And this is useful for doing maintenance scheduling or doing financial forecasting. And that remaining useful life estimate will change in response to varying conditions. And another very neat thing is process optimization. Now, this would use a similar technique, actually, to what self-driving cars would use. It'll take all the sensors that are positioned around in your plant and try to decide how to best optimize the next action for the plant. And whether you want to optimize for efficiency or optimize for throughput. And I would say that you probably wouldn't want to completely Skynet your plant, but by having this spit out a recommendation for you, it can help, you can then allow the operators to decide whether the action that the machine learning is recommending is a good recommendation or not. And of course, there has to be a feedback system whether an action is being taken or not. And that allows the machine learning to, over time, gradually learn how your plant operates, and what can actually optimize for certain things. Now, one point that I wanted to re-emphasize here is this is pretty long-term for both of these. It's going to take a while. You have to be patient for a machine learning algorithm to even achieve something like this. And that means that you have years of integrating machine learning into your workflow at your plant before you can reap benefits such as that. So since I've talked about the benefits now, I want to go over briefly some of the basic machine learning fundamentals and in how to make a machine learning program actually succeed. Now, you may have heard that machine learning and data science, those terms being used interchangeably. And that's because data is very, very important. And in not only just the raw data, but how you convert and adjust that data to be submitted to a machine learning algorithm will be important in creating something successful. So I'll talk about data and how machine learning looks at that data. But then I'll talk briefly about unsupervised learning and supervised learning, typically referring to both anomaly detection or classification. And it's just to help you peer into the black box a little bit so you can see what it takes to make successful program work. So the first step is always to collect very good data. And to decide what kind of data to collect, think about what analysts would need to collect in order to, say, determine the health of a motor pump drivetrain, right? You might want to have current transformers to take a look to diagnose any sort of electrical faults in the motor. Maybe you want to also have that current so you can evaluate the speed of the machine, especially if your motor is running on a VFD. Vibration, if you were here for the last talk, of course, is a great source of information for getting the heartbeat of the machine, and as is the differential pressure to evaluate whether your pump is operating correctly. Now, even more important than the amount of sensors that you have mounted on your machine is the quality of that data. Bad noise from bad cabling or having bad, poorly calibrated sensors are all going to contribute to garbage data. And garbage in is still going to be garbage out. So even for things like vibration, right? Vibration is challenging because not only is you don't just mount it, you have to think about how it's mounted, whether it's mounted axially or radially. In addition, also the type of adhesive you use to mount that sensor on, or if you're just using a magnetic mount, that'll change the frequency response of that sensor. So if we take a look at just vibration, for instance, this is a typical vibration waveform. And what an analyst would do is look for characteristics in that waveform, but also pull out certain characteristics, which I'm going to call features. And features are a term used in machine learning. In this case over here, maybe we could pull out the RMS, which is the root mean square, like the average vibration level. Also, you might pull out the crest factor, which shows how peaky or sharp the points on the waveform is. And both of these are features that can go into a machine learning algorithm. But of course, that wouldn't be enough for vibration. There's a lot more data here. Usually, vibration analysts will also look at the spectrum, the frequency spectrum. It's a transform from the time domain into the frequency domain, which creates a histogram that shows the energy that exists at each frequency bin. And from here, you can look at the running speed, harmonic, and then the harmonics of that running speed. And each one of those items can be entered into the algorithm as features. So if you take all that data and you place it into a chart, you'll get a matrix that looks like this, where the columns are the different features that you would decide to input, in this case RMS, crest factor, 1x level as an example. And the rows correspond to different data points at different measurement times. This is also where you would include a lot of other information to your machine learning algorithm if they exist, such as blade pass frequencies, gear mesh frequencies, if you are able to get that. And I wanted to stress this because the customers who have seen the most success with machine learning are the ones who are willing to put in the effort to find out some of this information. So this information is not always available on the nameplate on a machine. So getting that if you're able to get that information, then the machine learning algorithm will be able to track that information as well. So I wanted to, so once you take this data, now it's in a form that can be submitted to a machine learning algorithm, this 2D matrix of data that I'm showing you right here. And what the machine learning does with this data is essentially creates the scatter plot of that data. So on the left side over here, this is actually data from one of the air handlers at one of our customers' sites. And over here on the left side, I plotted the 1x harmonic versus the RMS. And you can see it almost basically creates a straight line because, and it makes sense because RMS, most of the waveform is comprised of the rotating speed. Meanwhile, if I plotted, say, the 1x versus a 2x, I get almost no correlation. It's just the blob of points. But what machine learning can do is not just identify the relationships between two different features. It can look at 3 different features. Maybe it can plot 1x versus RMS versus 2x. Even though I'm not creating a visual for you here, it's what it's doing. And it does even more than that, 4 dimensions, 5 dimensions, as many features as you want. It'll be able to analyze the relationships between multiple features simultaneously. Now here's where I need to give a warning. Making this work is not going to be as easy as just picking all the features you can possibly think of and throwing it at the algorithm, unfortunately. Because what happens is, especially if you don't have enough data, having an overwhelming amount of features is going to cause the algorithm to fit the data in a way that may not make sense. And I think it's best illustrated by an example. Say you wanted to make an algorithm, a machine learning algorithm, predict what type of car you would like, all right? But you're not a millionaire, so you only own 2 cars. And say both of those cars are tan. So if you use color as a feature into your machine learning algorithm, obviously the machine learning algorithm is going to think that you like tan cars, even if you just happen to pick those since they were on sale or something. Now if you had 40 cars, sorry, or maybe even 50 cars, let's say you had 50 cars and 40 of them happen to be tan, then the machine learning algorithm would be pretty accurate in knowing that you have poor taste in car color choices. But that's the point I'm trying to make here is that it's not as simple as just throwing any feature you want. It's important to have domain expertise in order to pick the correct features that will make the machine learning program operate correctly. And so if someone, say, from last talk I was mentioning, someone from Silicon Valley comes up to you and says that they have a stock picking algorithm that picks good blue chip stocks, and they say, oh, you can also use this for your application. I would probably ask a few more questions about it. Actually, given this, now that you know that how machine learning looks at these data points, I can kind of explain to you then how this is actually better than just using basic alarms. Because say over here I have, on this left side, I have one feature plotted against another feature. And this could be anything. This could be temperature, let's say, and this could be pressure. Now let's say that in normal operating conditions of this machine, the data points form this odd L shape. These are all normal conditions, but the relationship between pressure and temperature just happens to be this way. Now, if you just use alarms will just set it on a single sensor, right? So you'll have one alarm here, and you'll have one alarm here, which forms a box. And boxes are not even typically how sensor data relationships are anyway. If you have a red point over here, this looks anomalous to us because it's not fitting into this shape. The alarms are not going to pick that up. And then similarly, if we look over here on the right side, we have maybe two different operating conditions. This is very common. Some machines will operate in two different states. And you'll have one cluster of data here and one cluster of data here, which is healthy. But then some of these other points are not healthy. The alarms can pick up, they say this orange point here, which is outside of the boundary, but there are other points that, that these basic alarms just won't capture. Now, machine learning is capable of drawing a more complex boundary. It can draw a boundary that surrounds the points more accurately, and you can adjust how tightly you want to fit the curvature of the data and also where the offset is. And so to give you, see a little bit how this works, I want to talk about anomaly detection. One common algorithm for anomaly detection is one-class support vector machines. And say over here I have some data, again, it could be any features, it's not really important. And I have the blue points here are the data early on when it's very healthy. And the red points are every other piece of all the other data points that I want to evaluate the health of. What OCSVM, one-class support vector machines, is a distance-based algorithm. So once I supply the algorithm with these set of blue points here, the healthy baseline, it'll draw a boundary around it. But note here that even though I've drawn it in 2 dimensions, this plane is actually in multi-dimensional space. It's a hyperplane or a hyperellipsoid. And now what we can do is evaluate points based upon whether it's inside of that boundary or the distance away from that hyperplane boundary. And as you look, you can base the health of whether it's moderate, severe, just based upon that distance. Now, if we look at the machine health score, this health score is just a plot of those distances. You can see over here that it starts off as green, and it fluctuates between yellow and green before finally ending up in the yellow area. And if we take a point from the healthy area, you'll see in the spectrum that the vibration spectrum looks very healthy. And if you look at the unhealthy portion, you'll see a very high one times peak. Because remember, this health score, oh, oops, wrong button. This health score is taking into account a bunch of features simultaneously, the 1x, 2x, the RMS, like I've said. Another nice feature that some machine learning algorithms offer is the ability to pinpoint the features that are contributing most to an unhealthy score. So for instance, that point that I had pointed out earlier, the 1x level is very high, and the algorithm that you're using should point out that 1x level being very high. Later on, perhaps the noise gets a little bit worse. The algorithm can point out to you, hey, there's high 1x and high noise. Maybe there's some sort of cavitation. Now I want to just skip over this to talk briefly about classification. Okay, so classification is really useful in identifying different states that a machine is in. Now, this particular machine, this cooling water injection pump that we were looking at, I've taken the multi-dimensional data. I've used a technique to reduce it down into 2 dimensions so that you can see it plotted here. And you can see a few distinct clusters. In the location where this pump is located, in the winter and spring, it doesn't have to work as hard as in the summer and fall, so the values end up being a little bit higher. But these are both normal operating conditions of the pump. And that's something that band alarms can't necessarily capture. Meanwhile, these over here are actual anomalies. I think this one was actually misalignment, I believe. So anyway, if you can provide a labeled data set to your algorithm, you can train it to be able to determine these different states. And this is useful for whichever any sort of machine that operates in various states or clusters. For instance, machines with VFDs will regularly switch speeds, or machines that have varying loads. So I'm going to skip over just a couple more things for the sake of time and just give an example of how you would actually train a machine learning algorithm to recognize something like imbalance. Here we have data coming from a machine where there's actually imbalance, and we did confirm that there was imbalance on this machine. And the way to train, what a data scientist would do is take a portion of that data as input. It needs to contain both healthy and unhealthy data, data with imbalance. And that would be submitted to the classification algorithm, it would create that function, that rules-based function that I was mentioning, to determine whether something is healthy or unhealthy. And lastly, I would take the remainder of the data to test to determine what the accuracy of that is. And vibration science, like I said, shows up in very distinct patterns. And that's really nice because it helps the algorithm. We find that classification algorithms tend to be very accurate in classifying some of the major faults, such as misalignment or imbalance. So I'm going to take the remainder of the last bit of time before questions to go over the key takeaways of, that I want you to see through this presentation. And the first is to recognize the advantage that machine learning offers, which is that you can look at multiple sensors and the relationships between them simultaneously. And especially with a bunch of new sensors being placed in your plant, having that will be very useful in helping your analysts focus in on the particular areas that need more further examination. And if you instead had to hire a bunch of people to do that, it would take an enormous amount of people to evaluate all that data. The second thing is that I wanted to stress the importance of data. Of course, the more data you have, the more accurate your algorithm becomes. And you can leverage some technologies that are out there. But be careful, because you shouldn't just necessarily just use the cheapest sensor available, because the quality of the data, like I said, is very, very important. So making sure that data quality is good and coming in properly is why I say machine learning is kind of a journey. It's not necessarily difficult to implement machine learning at your plant, but it's not going to be a one-time thing. It's something that has to be integrated into your typical workflow. So if, say, a machine goes out for repair, the machine learning algorithm should have visibility into that. Say you switch out an impeller on a pump, but the machine learning algorithm still thinks that it has the old impeller. It's not going to be able to properly determine faults in that category. So it's a journey, but if you stick with it and you have the patience to make sure that that the machine learning algorithm is getting all the information it needs, you can get some of the benefits that come with that, like I've discussed, such as process optimization. And I'm going to stop right there because I think I'm hoping you guys have some questions you wanted to ask.
Okay, so these are tapes, so be patient. I'll have to bring the mic when you have questions. Okay? I got a couple. I got one over here first.
Thank you. Hello, I'm Preston Johnson with Allied Reliability Group. I'm a platform lead in intelligent monitoring. Mm-hmm. From a vibration analyst perspective, which I've had some training there, I would look at a number of vibration sensors on something like a motor pump. I would calculate 10 or 15 condition indicators off of each one of those sensors, and then I'd be looking for some combination. I probably have 150 or so features. If I'm getting started, could I use can you just start feeding data in, call it normal, and then machine learning will find an anomaly that I can then go identify? Is that a reasonable approach?
Yeah, somewhat. Like if I go back to this example here, right? You would have to indicate a healthy baseline in this case, yeah. And when an anomaly is detected, it's going to be detected based upon a number of features simultaneously. And so, the short answer is yes. And it's nice because, like you said, even though the anomaly detection is not going to say exactly what caused it, it can highlight certain features. So in your case, probably either like certain bins in the frequency domain or certain sensors that seem to contribute most to that anomaly. And then you can like focus in on those particular sensor, that data, and see if you can come up with any good diagnosis.
My name is Gopal with OSSF Pi System. My question is, how are you converting all these features into a single health score?
So people will do that differently. It's so the data that we take, we actually don't just simply take this, like the chart that I'm showing here. We don't typically just put this data in directly. We'll actually do some, we'll look at the features that vibration analysts will look at. Our company right now mostly focuses on vibration. So then I'm going to talk in that realm mostly. And we have the data typically for just a single machine train. And we'll take a bunch of features from the spectrum, and we typically do some sort of feature reduction technique, which I won't go into here. But that data is then fed into the anomaly detection algorithm. Was there an add-on question to that? No. Sorry.
Can you speak to that feature reduction technique?
I think we can talk about that. We can talk about that offline if you like.
Okay.
Okay.
Hi there. Good presentation, by the way. Thank you very much. So my question relates to one of your first slides where you showed the whole process from loading of a fuel to whatever it was, power plant or something. And it illustrates the fact that even though you have many features, but there's a time delay between them. When you correlate two features, they don't happen at the same time. How does that work?
Right. That's a good question. Yes, the time is going to be, of course, very important. The timestamp is going to be very important in coming to a decision based upon that. Hopefully, we can get to a point where the data is coming regularly enough to where that wouldn't play as much of a role. But yes, if the time isn't happening simultaneously, it's not going to. If the measurements across the plant are not happening like at a fixed time point, then yes, that would change things. You're absolutely right. So it's important to make sure that that happens.
I have a question then. Can you set those parameters?
Yeah, you can. Well, that depends on the system that you're using, whatever product you're using to collect data across your plant. There are wireless technologies out there which use like a cloud-controlled measurement interval, and so whenever the sensor connects, it receives the information. Oh, I need to collect information at this particular time, and then it can then collect at that particular time.
Great. I got one here first.
Yeah, I'm Abdul Ghamdi. Is it similar to the advanced process control concerning the process optimization, sort of?
Sorry, could you repeat that?
In the petrochemical industry, they are using advanced process control to do a better optimization for the plants, and they are collecting many data to get one output. I know this is from machine point of view, but from process point of view, there is something similar like APM, advanced process control.
Oh, that's really interesting. I'd love to talk to you later about that. I don't know as much about that in particular. It's certainly possible. I'm not sure. Sorry about that. We can talk later about it. I'd love to hear more about it.
Okay. Another one?
Hi, my name is Matthew Furry. I work for Tetra Pak in Sweden. I wanted to find out from you, in the company that I work for, we do carton packaging. And we're also looking into machine learning to try and understand, the remaining useful life of certain components that are high-cost contributors. And one of them is in induction heating that we use to be able to seal the packages. What I see demonstrated over here is only a single area of collection when it comes to the features, vibration. Do you use other data sources as well too from other monitoring that you have on the equipment to be able to gather all these features, to be able to make a conclusion as well? We've looked into that, so I just wanted to find out if you've done any investigation with your company, with customers from before.
Well, I don't think you probably don't know too much about our company. Our first product is not a sales thing. I'm just telling you that our first product was a vibration sensor, wireless vibration sensor. So most of the focus, like you said, has been mostly on vibration. We are looking into integrating other sensors into it, so we're looking into that. But I don't have any examples of that as of yet. Yeah, but I think that it should. Overall, I think that it should work. You might have to do some sort of clever feature engineering with that as well.